All right. So we're getting ready to actually move out of kinematics just for a little bit. There'll still be some times when we need to actually use kinematic equations and everything, but we're actually getting ready to start talking about energy. And this first lecture will be a discussion about kinetic and potential energy and how those things are conserved and how they change over time. So we'll still be looking at how things move, but instead of looking at it through the lens of forces and how forces are acting on objects, we're actually going to look at it through how the energies of these objects are changing. But we're still going to be doing essentially very similar problems and coming up with very similar statements and understandings about the same systems that we've been looking at. Oops. Right. So essentially, there are two fundamental forms of energy. Well, let me fix my chair. There we go. Okay, so there are two fundamental forms of energy. You have kinetic energy and you have potential energy. So the whole idea here essentially is kinetic energy, with kinetic coming from like the Greek word, I think, for like motion and movement. So we have kinetic energy, which is the energy of motion. So it's associated with how something is moving. And then we also have potential energy, which is an energy associated with a position. So essentially, how something is situated is going to tell you what the potential energy of that object or that system is. So the cool thing is that this is one of the greatest scientific discoveries, is that the whole idea of energy, and objects have energy, and that energy can be transformed. So it's worth noting that this is a really important idea. It actually took a while to figure this out because this isn't like something you can see and come up with. Just like over time, Newton came up with the whole idea of Newton's laws and forces. Energy is not that intuitive. It's really hard to see, and I think you all will discover that as we get into some of these example problems and these new concepts. So it is important to understand how energy can be stored and transformed from one form to another. So this is almost just like accounting now. We're just looking at energy in one situation, and as that situation changes, how does the energy change? So it's really worth thinking about this like you're accounting like with money or something. Okay, so that's the most basic way to think about this. Energy can also be transferred into or out of a system, and it can also be transformed within a system. Okay, so we have transferred in and out, and we also have transformed within. So we have external energy coming in and out, or the energy that's already in the system. We're going to do several different things with that. So the whole idea that nature conserves energy is one of the most important concepts in science. Like you see this idea of conservation of energy everywhere, in biology, in chemistry, in astronomy, in the physics that we're doing in engineering. It's one of those universal ideas that shows up a lot. So these ideas about energy also extend to heat, chemical energy, and molecular energy. So when you think about molecules moving back and forth, like those springs we talked about, same thing. So that's also worth noting. There's a delay. There we go. So let's talk about motion, position, and energy. So let's use something we're familiar with. Let's talk about this ball here that is in free fall. Okay, so we got this ball over here on the left. It's in free fall, which means it's moving only under the force due to gravity, right? So its acceleration is just negative g. We know that because it's accelerating, its velocity vector, as you can see here, is going to increase over time because it does have that acceleration. So just like in previous lectures, we're going to consider the before and the after pictures of this familiar free fall situation. Okay, so there is one kinematic equation, if you think about it, that relates the before and after information without regard to time. Okay, so you'll remember like the 1/2 at squared or velocity times time and all those equations. Most of those have a time component except this one. Remember where the velocities initial and final were squared? Let's actually utilize that fact that we have this initial and final without regard to time. So if you look at the kinematic equation that we used quite a bit without time, you'll notice that there is a final component and there is an initial component. But now that it's not quite separated yet. So let's think about this just a little bit more. We have this delta y, okay? Now, if you remember, the delta just means final minus initial. So in fact, there's actually more final stuff and initial stuff nested in this equation. So what we can do is we can actually just rearrange this equation, okay? And we can situate it such that all the final stuff and the initial stuff are each on a different side of the equation, okay? So we can fully separate this. So let's do that. So down here, I'm going to split the delta y. As you can see, the y final minus y initial, okay? So this is the equation we're starting with essentially. Okay, now once I separate that, I can distribute the 2a through, okay, and you can see I've done that over here. So same equation, just done some algebra. All right, now here's the trick. So what I can do essentially is just do a little algebra and I can get my final information on one side and my initial information on the other. So you can see it's the same thing on both sides of the equation after I do a little bit of algebra. But let's see. Right here. So we have the same thing. We have this v final, or no, sorry, we have a v squared, so velocity squared plus 2gy. So whatever that is at the beginning, it's the same before, okay? So whatever that is before, that has to be the same after. So this is actually a conservation law. So it turns out that this v squared plus 2gy is actually a conserved quantity. Okay, so apparently there's this like v squared and this, you know, change in y, this thing is conserved. Let's see if we can bring Newton's second law into this to see if it helps us understand this a little bit more. So let's apply Newton's second law to the free fall problem that we just talked about in the last slide. So we know that Newton's second law, which I'll abbreviate through this as NSL. So Newton's second law is just force equals mass times acceleration. Okay, well, I'm going to rewrite my acceleration. I'm going to write it as dv dt. We can totally do that. That's an old definition. Well, our acceleration, or our dv dt, is actually just negative g because this object's in free fall. So I'll leave that note here. So our change in velocity over time is just negative g. Now let's use a math tool here that you may have seen if you've had Calc 2 already. So here we're going to actually use the chain rule to rewrite Newton's second law here. So what we want to do is we want to think about just the acceleration, just the dv dt. So remember, this is our acceleration. All right, so what's going to happen here is we're going to say, well, dv dt, since everything is continuous and differentiable, there's no weird breaks in this function because nature says it has to be a nice continuous function. If that's the case, we can treat these little differentials, the little d's, the dv, dy, dt, we can treat those actually as little numbers in a fraction here. So look at what I've done. I've essentially taken the dv dt and I've rewrote it to include some extra terms. So I've dropped, I'm going to see if I can change my color here. So I've essentially multiplied by dy over dy, as you can see here. Okay, so well, what does that give me if I multiply by a dy over a dy? Well, that's essentially multiplying by 1. All right, so if I multiply by 1, I can actually just rearrange these. So I can put the dy, the denominator, over here. I can put the other dy, the numerator, over here. So the intermediate step here, I guess, to make this super clear would be having a dbt times dy over dy. Okay, well, I can totally do that, and I can move things around, essentially switching the bottom. But look at what that's given me. Okay, so I've multiplied by 1. I haven't changed my problem. But I've also, instead of having a dv dt, I now have a dy dt. Well, that's instead of a change in position or a change in velocity over time, I have a change in a position over time. Well, that's just a velocity, dy dt. That's the vertical velocity. So you'll notice I've marked it here in red. This dy dt is actually just my velocity, but I have a few extra dangly bits now. Now I have this awkward dy or dv over dy. But I can move that along with me. This comes along for the ride. All I've done is just change the denominator here. But now think about what this is saying. This is saying we have a velocity v times a change in velocity over a distance. So instead of your velocity changes with time, you have your velocity changing with some distance. Okay, well, that's all well and good. So what I'm going to do is I'm going to replace my acceleration, my dv dt. Okay, I'm going to replace it with this v dy, or sorry, v dv dy. So really, that is just a. I've just stuck it in here in this really interesting new form. And we also know that this mv dv dy also still from the top here, that still equals negative mg. Okay, so we've rewritten Newton's second law here. I've got it in green. We've got this interesting new statement, but it's still just Newton's second law resting in there. But here's the interesting part. We can actually look at this, look at these differentials, and because all these functions are nice and continuous, there's no breaks or weird kinks in these functions. What we can do is actually just multiply the dy over, and we have two little statements with two differentials on the end. So we have mv dv, and then we have negative mg dy. Now you might notice this is actually starting to look like an integral. And that's exactly what we want. Okay, so we have this statement here. These two statements with some differentials on them. Now we can actually integrate this. So we can integrate from before to after, just like we've been talking about. So the before is going to be the initial stuff. The after is going to be the final stuff. Okay, so over here on the left, we have a velocity, so we want to integrate from a vi to a v final, so initial velocity to a final velocity. On the right, we have a dy. We have a vertical position, because remember, this is the object in free fall that we're talking about here. All right, so now we're going to integrate from this final or initial position to final position. So let's go ahead and do this. We'll solve it. So the integral of v dv, well, we know that this in here is just going to be 1/2 v squared. For those of you that are familiar with integration, you've hopefully seen it by now in Calc 1. If not, you've definitely seen it in Calc 2. On the right-hand side, just in the integral, we have the integral of just some constant. It's just 1 in there, right? We know it's not 0. We just know it's essentially a generic 1. So when we integrate this, that's just going to give us this difference. Oh, no, let's make it even more simple than that. I'm going to erase this. So when we integrate a constant, just thinking about the integral here, we know this is just going to give us y. Okay, now we've integrated these. We still have to deal with these limits of integration, the v final, the v initial, the y initial, the y final. Okay, so you can see after we've integrated and we brought those constants back in, here's our first integral. Okay, I put all the stuff on the left in green, the stuff on the right in blue. So here I've integrated, I got my 1/2 v squared. I'm remembering the mass out front. Okay, I put that back in. Now I just have to evaluate this using my limits of integration. And we know we essentially plug in our first limit, so v final, the one on top of the integral. Okay, so we plug that in to whatever our integration is, and then we subtract the other one, so the vi. And it's just, when we evaluate the limits of integration, it's just the difference between these two values from the original integral problem. Okay, so that's 1/2 mv squared, the final, minus 1/2 mv initial squared. Same thing on the right-hand side. Integrated, I got my y. I made sure to bring in that mg from the outside, the negative mg, don't forget the negative, okay? Now I'm going to do the same thing. It's going to be the y final, so that my top limit on my integral, minus my bottom limit on my integral, so the y initial. So I'm just plugging those in to the outcome of my integral. Now you'll notice I flipped the signs here. So here I have a negative and a positive. That's just because I brought that negative mg in. So the negative that was already up front flipped those signs. So that's the negative I'm talking about there. So if you're wondering what happened with those signs, just go back and remember that there's that negative already at the beginning. Okay? So now we have some final and initial stuff equals some final and initial stuff. So let's see if we can combine this. So what I'm going to do is I'm going to take, I'm going to take my final here, and since it's a minus final stuff, I'm going to add it over to the other side. And then same thing, but in the other direction. I have my initial stuff here. I'm going to add it over to the other side. And what that's going to do is going to put all my final stuff on one side and all my initial stuff on the other. Okay, so I have my before terms. Before terms are here. I mean, you can write it in any order you want to. And then my after terms are over here, just as long as you group them. Now, something really cool happens here. Notice, just like in those previous problems we talked about where we approached this with our kinematic equation, look at what we have. In both of these, we have a v final squared plus final position, and then we have a v initial squared in both of these, and then position squared. So what's really interesting is that conservation law we talked about at the beginning, where the velocity and position was conserved. We're doing the same thing here. We just have slightly different numbers out front. So notice the coefficients are different, but those core values, the velocity and the position, those are still conserved. Okay, so now we have this new equation where we have some final stuff equals initial stuff. Each side, the left and the right, has two terms. Let's actually give these terms some names. So remember, kinetic energy, that energy of motion. Well, it looks like we have a excellent definition here for this piece of the equation that deals with motion. Okay, so this 1/2 mv squared. So that's actually the initial and final kinetic energies. And this is just how we define kinetic energy. It's 1/2 mass times velocity squared. Okay, remember, kinetic energy deals with motion, therefore the kinetic energy depends on the speed of the object, the speed of the particle. If we say particle A has a kinetic energy, that means it has to have some sort of velocity. Now we can do the same thing when we think about the potential energy. So remember, the potential energy deals with position of a particle. Okay, it doesn't have velocity. It could and still have potential energy, but we're just honing in on where the particle is and how it's situated. Okay, so that's why we're going to define the potential energy as the mgy terms. Okay, because that has the y in there. That has the vertical position in our case, but later on we'll see some potential energies that deal with x, like side to side. So for right now, we have this kinetic energy dealing with motion and this potential energy that deals with essentially where a particle is. So you'll see here, and this is important, if we take the final kinetic energy and final potential energy and add that up, that's going to give us a total energy, and that total energy equals the same amount that we started with. So that this is the whole idea that the total energy in the system can be the same, but the kinetic and potential energy, they can be transferred to each other inside the system. Okay, now there's a couple of things here you need to notice. So the energy is not a scalar. Sorry, energy is not a vector, but it is a scalar. Okay, so energy doesn't really care what direction it's headed in. It's just a value that you can assign to a particle. Also, you should notice that kinetic energy is never negative. And if you look at the definition, that makes sense. It makes no sense to have negative mass, right? Unless you're talking about dark energy, and we're not doing that here, or dark matter. That's a topic for an astronomy course. So everything we deal with, mass will always be positive. And then even if an object has a negative velocity, it's squared. A negative number squared is positive. So whether your velocity of this particle is positive or negative, as soon as you square it, kinetic energy is positive. Okay, so now the big question is, what are the units of energy? Okay, we have these two new definitions. Okay, they're physical properties of the system. We need to be able to talk about them as far as like the units, what the units represent, and what they're telling us. So if you think about it, as far as kinetic energy goes, kinetic energy is mass multiplied by a velocity squared. Okay, so we have kilograms for mass multiplied by velocity squared, and velocity is meters per second. Well, we can square that and distribute the distribute the square. So it's meters squared per second squared. So here we have kilograms meters squared per second squared. You could also think about this as kilogram meters per second squared. So we know this is a Newton times 1 extra meter. That 1 extra meter on the outside is actually going to give us that extra meter squared per second squared in there. So you could write this as a Newton meter, or we'll get to the other name of a Newton meter shortly. So just from looking at kinetic energy alone, we decided that we could call these Newton meters, which is totally fine, totally valid. Let's do the same thing with potential energy. So with potential energy, we have mass multiplied by acceleration multiplied by position. Okay, so we're multiplying 3 different things here instead of just 2 different things like in kinetic energy, but let's see what happens. So we have mass, kilograms, multiplied by an acceleration, that'd be meters per second squared, multiplied by another meter. Well, look at that. We have kilograms meters squared per second squared. So even though we have 2 different sets of variables we're multiplying together, we get the same thing both times. Okay, so it turns out that this value, this kilogram meter squared per second squared, which is a Newton meter, this is a Newton meter, well, this value is also called a joule, okay? So 1 joule has the units of kilograms meters squared per second squared, which saying 1 joule of energy is easier to say than 1 Newton meter of energy. It's just less words. You should note that mass must be in kilograms and velocities must be in meters per second before doing any calculations. This is one of those times where the units are really going to matter. So do keep that in mind. So now that we actually have these definitions of what these things are, kinetic energy, potential energy, let's actually talk about some energy bar charts here and how we can actually do the accounting that we talked about earlier as far as like keeping track of what has how much energy. So let's look at this simple example where we have a pebble tossed into the air, okay? So when the pebble is initially tossed upward, it has no gravitational potential energy, okay? The initial energy is all kinetic. And you know this from kinematics. When an object leaves the ground, it has its maximum velocity on the ground, but as it reaches the top of its arc, or if you're just throwing it straight up, as it reaches the top of its trajectory, well, gravity is slowing it down, right? Eventually it's going to get to the very top and it's going to have, for just a moment, a velocity of 0. Okay, well, we'll keep that in mind while we look at how we can think about this through energy. Okay, so we said initially, okay, so over here, let's look at this first frame number 1. Okay, so right here, energy of motion, kinetic energy. Okay, we'll call this Vmax. This is where it has its maximum velocity. Okay, so right here is our origin. 0 meters, it's not went up yet. Okay, so here all of its energy is kinetic. It's got this huge velocity going up, and that means it has all kinetic energy. It's not moved in the y direction at all, which means there's no kinetic or there's no potential energy there. Now, eventually, this ball is going to get to some sort of halfway point where it's got a mix of both. It's moved up. It's gained from 0 meters in the y direction, right? So instead of being down here, it's got some new y value. It's not its maximum height, but it did have some positive movement. It gained potential energy, gravitational potential energy specifically, as it was thrown upwards. You'll notice that its velocity vector is a little bit smaller now. So some of that max velocity that it started with actually got changed. Okay, less kinetic energy, slower velocity. Some of that is actually getting changed to potential energy. You can see that here in the plot. So the kinetic energy bar is getting smaller and the potential energy bar is getting bigger. So there's starting to be this trade-off between energies. Now, when this pebble gets to the very top here in 3, when it reaches its maximum height, its speed is briefly 0. We know that. Okay. So its speed is briefly 0. Okay. And all of that Vmax it started with got transferred to potential energy. Okay. So this is all potential energy, capital U. And you can see that here in the energy bar plot. The kinetic energy, there isn't any, it's zero. And you'll notice that this initial kinetic energy here and this potential energy here, the bars are the same heights. Are the same heights. So that means the same amount of kinetic energy we started with gets converted to the same amount of potential energy here in the middle of the problem. And now as we go to panels 4 and 5, we're just going to see this same thing happen in reverse. All that kinetic energy gets split, all the potential energy gets split between some potential and some kinetic when the ball is coming back down to hit the ground. Or sorry, when the pebble, I guess, is what we're talking about. Okay, so as that pebble falls, in these intermediate places, we're going to have some of both types of energy. And then by the time it hits the ground, again, we have y equals 0 meters. There's no height. There's no gravitational potential energy. So you'll see that in panel 1, the ball started with maximum kinetic energy, completely transferred it at its peak to potential energy, and then took all that potential energy and transferred it back to kinetic energy by the time it hit the ground. Okay, and you'll notice, and it's written here, but I need to highlight it to make sure you see it. At any given moment, the sum of the kinetic energy and the potential energy is always the same. So here, you'll notice if we take these two bars, if we take all the kinetic energy and add no potential energy, we reach this threshold here, this total energy value. If we were to take these two bars in panel 2 and add them together, they would perfectly stack to reach that exact same height where I've drawn my black bar. Same thing over here. We could take all of the potential energy and add 0 kinetic energy, and we're up there at the same height. And this, you can just keep going on and on. So the whole idea here is that the total energy in that system remains the same. Okay, that's actually really important. Now, something you may be wondering is like, well, how do we know how to pick our origin for these problems? That's actually a good question. Clearly, depending on where you put your origin, it's going to change how much potential energy you have. So let's look at this example here of Amber and Bill, who use 2 different coordinate systems with 2 different origins to determine the potential energy of this rock. Okay, so we see that Amber here, her origin is on the ground at 0 meters. Okay, and her rock actually starts with an initial potential energy, a gravitational potential energy, because she starts the rock at 1 meter above her origin. Oops. Okay. Let's go from current. Okay, so this is started right above. Now, Bill here actually starts the rock at his origin, which he defines to be 0 meters here, where the rock starts, not where the ground is. So he's actually going to, I'm going to change that back to black. There we go. So Bill's actually saying, well, this rock has 0 joules of energy at the beginning and then winds up getting a negative potential energy at the end. Okay, so do note that placing the origin of the coordinate system does allow us to pick the 0 of potential energy. So really you want to say at some height, this is where my potential energy is going to be 0. Now look at what happens. here in the energy bar charts. Okay, so let's do amber's first. So yes, amber does say 0 kinetic energy at the beginning. Totally makes sense. It's not moving. Okay, the only thing in amber's case this rock has is potential energy, because it is 1 meter up off the ground. Okay, so here's her initial potential energy. Now, what she's saying is that at the end of this, when she drops it, all of this potential energy is going to get converted to kinetic energy. Totally right. Which means there's going to be no potential energy left over at the end. Okay, now Bill, let's see what Bill's going to say. So because Bill put his origin up here where the rock starts, well, he's removed the potential energy from the rock, from his reference frame. Okay, so he has no potential energy. He also has no kinetic energy in this rock because it's not moving. But so here's the weird thing. So he starts with a total of 0 joules of energy. Okay, and when he releases this rock, well, think about where it ends at. So it's actually going to end minus 1 meter below where it started. So when this is over in the final situation, it's going to have a negative potential energy. Okay? Well, here's the thing. It gets a negative potential energy, but it also has a velocity when it hits the ground, right? So in Bill's situation, this rock has 2 different energies. It's got its kinetic energy when it hits the ground, but because it did move from the origin, it also has a negative potential energy. So we have positive kinetic and then the negative potential. But look at what happens. These cancel. If we have the positive of the kinetic and then we add the negative of the potential, we still get 0 joules. So these actually cancel and we still get 0 joules. So the beginning and the end of the problem still match. Just like in Amber's case, the total amount of energy is still the same on either side before and after. It's just we've got different types of energy. You can see with Bill, he's got a mixture of kinetic and potential. So although Amber and Bill may have different values of potential energy at the beginning and the end, notice that they still calculate the same difference, the same delta U, right? So the same final minus initial. So I'm going to draw that here in orange. So here, just for emphasis, I've colored in Amber's potential energy as orange. So she starts with this amount of potential energy, and then she loses it. This amount is subtracted out because over here at the end is 0, is flatlined. All right, now let's look over here at Bill's setup. So Bill starts with 0 potential energy, but that same amount, right here I've colored in orange, that same amount is still subtracted out. So in both cases, you can see that this same amount, it's the same amount is subtracted. So it really doesn't matter where you put your origin. You might start with a different potential energy, or you might wind up with a different potential energy, but your change in potential energy is the same no matter where you put your origin. So that's key here. If y'all are working on a problem set and maybe 2 or 3 of you have different places for your origins, you'll notice that your potential energies they may be different, but when you calculate that delta U, that final minus initial, you should all get the same value. All right, so we've talked about things in free fall. Let's talk about gravitational potential energy along a path. So let's consider Newton's second law for a particle being pushed up a ramp. Okay, we've done lots of these, so you know how they work. So we have the x-axis, okay, which follows an incline. Okay, so instead of like an an s-axis, so instead of an x or y-axis, we'll use the generic s. Okay, so once again, let's use this chain rule. So here, just to sum up everything really quick, we know that this object is not flying off the ramp or sinking into the ramp. So really all we're worried about is the sum of the forces in the horizontal direction. So I'll just say the x direction here. Okay, so we know since it's being pushed, we have the net force equals ma, which is just dv dt. We're going to do the fancy chain rule again. So we have vs times dv ds is the same thing as dv dt. Now, we need to add up the forces, and if we look down here in our free body diagram, you'll see that we're just worried about friction right now, okay? So that's going to be negative mg sine theta. That's the only force we're dealing with. Okay, so the net force, all the forces summed up, is just negative mg sine theta, and then all this is going to equal this new funky way of writing Newton's second law. Now, watch what happens. We can rearrange this just like last time, okay? And then we have this dangly bit, this sine theta ds. Now, if we consider the geometry of the situation, and we look down here at the bottom right, okay, we see that the dy, the vertical piece here that I'm highlighting, dy is really just sine theta times ds, okay? Because that's just the opposite over the hypotenuse. Well, the opposite is dy, a little change in height. And then the hypotenuse, that's just a little change along our x-axis up the ramp. So a little ds, okay? And that's where this sine ds comes from, okay? So turns out dy equals sine theta ds. We can totally do it. Just a geometry problem. So now I'm going to take that sine theta ds and just rewrite it as dy. Okay, now taking that same statement, I'm essentially just going to integrate again. Same thing as last time. Pull out my constants and integrate. And you'll notice by making that substitution, I get the same thing again. I get my kinetic energies over here. I get my potential energies over here. I can put all my final stuff on one side, all my initial stuff on the other, and I get the same thing. Notice how the sine theta did not matter. Okay, so I get the same equation as the free fall derivation. So what does that mean? I had something in free fall and I get these equations. I have something like sliding down a ramp and I get the same equations again. So it turns out, as long as energy is conserved, if you have a particle moving along any frictionless surface, regardless of the shape, the equations are the same no matter what path the particle takes. So that means the particle could go up a ramp like this. It means the particle could go up a ramp like this, As long as everything's conserved and the surfaces are frictionless, energy is always conserved. It doesn't matter what kind of path you're taking to get from point A to point B. All right, so let's talk about the conservation of mechanical energy. So we have K, which is the total kinetic energy of all the particles in the system. Okay, we have U, which is the total potential energy of all the particles in the system. Okay, we have these things added up, the K plus U, the total mechanical energy. And we know that this, provided there's no friction, doesn't change. Okay, so this is the law of conservation of mechanical energy. Okay, so it shows us that if there's no change in mechanical energy, then we have this interesting statement here. a change in K equals the opposite or the negative change in U, okay? So this is true on frictionless surfaces. And essentially, if kinetic energy is gained, potential energy has to be lost, and if potential energy is gained, kinetic energy has to be lost. So the gain in one has to equal the loss or the negative of the other. Okay. And again, just to reiterate, the kinetic energy is associated with motion, and the potential energy is associated with position. Kinetic energy, as we've shown, can be transformed into potential energy and vice versa. And under some circumstances, frictionless, the mechanical energy is actually conserved for a system. Okay, so now I want to walk through an example and then we will call it. So if I do run over in this lecture a little bit, I apologize. The following lectures will actually be a little bit shorter, so bear with me. So here we have a 10-gram bullet, which is fired into a 1,200-gram wood block, okay, and it's hanging from a 150 centimeter long string. The bullet embeds itself into the block, and the block then swings out to an angle of 40 degrees. So what is the speed of the bullet? Okay, so we want to know the incoming speed here. So we have this bullet, and I'm going to draw over my arrows already here. We have this bullet that hits this block. It embeds itself, and then this block swings out by 40 degrees. So this is a neat problem where we can actually take that deflection, that 40-degree deflection, and all these parameters, and actually calculate the speed of a bullet with it. But first, there's some things we need to notice and think about here. Okay, so first, the bullet and the wood block undergo an inelastic collision. Okay, so they do stick together, and this, as you will recall, is a conservation of momentum problem. So we have momenta from the bullet. These things collide, they stick together, so they have a common velocity, and they're going to act like a single object after the collision. Okay, so this new combined object goes against gravity. Okay, so we have kinetic energy that's being transformed into potential energy. Okay, so that K is going to be converted to U. K is converted to U. Okay, because we're going to gain some potential energy here. Okay, so this part is also a conservation of energy problem. Okay, so here's our collision initially where it was a momentum problem and momentum transfer, and then this swing and the increase in gravitational potential energy, well, that's an energy problem. Okay, so here we have to use both concepts. Okay, so first let's think about it from the momentum perspective. Okay, so let's consider the before and after of the collision. Okay, this is just the first part where the bullet hits the block. Okay, so remember that the initial velocity of the bullet is the thing we're after here. So the objects are two different things before, and then they are combined after. So the final velocity is actually a common velocity between both objects. Okay, so let's set this up. We have the momentum of the bullet, and then we also have the momentum of the wooden block. Those are separate. Remember, the velocity of the block at the beginning is 0. So that whole term goes away. The block's not moving. And then afterwards, we have this combined mass at the end because they're acting like one object. And we don't have to worry about separate velocities because this one combined object only has one common velocity. Okay, now, since that velocity of the wooden block is 0, we can easily and quickly just solve for our velocity of the bullet here. Okay, so look at what we get. We actually get a nice little expression. So the velocity of the bullet, which is what we're after, equals the total mass divided by the mass of the bullet times the final velocity of these things. Okay, well, there's one problem. We don't know the final velocity. See, this is the thing we're after. We want the initial velocity of the bullet, but we need to know the final velocity of these things together in our calculation. So we have two unknowns here and only one equation. So let's jump over here and think about the energy in this situation. So the initial speed of the energy problem, okay? So now this is the new problem where they've become one object and they're swinging up. So the initial speed here of this swing is actually the final speed of this momentum problem. Okay, so whatever the final speed is here is going to lead us into the initial velocity or the initial speed of this energy problem. All right, so assuming the system is isolated, which is fine, we know that the energy will be conserved. Okay, so all the before stuff and the after stuff will have to equal each other. Okay, well, the before stuff, the initial stuff, this block hasn't swung up yet, so it hasn't gained any potential energy. So we know that's going to be 0. It probably has a lot of kinetic energy because it was just shot with a bullet, so there's its kinetic energy. And we know all of that is going to get turned into a final gravitational potential energy. Now, at the end, at the after part, this block's going to swing up, and when it reaches its peak, it's going to have a velocity of 0, a final velocity of 0. Okay, the final velocity is 0 meters per second, so we know its final kinetic energy is 0. Now we're just left with all the kinetic energy equals all of the final potential energy at the end. Okay. All right, so the block begins with the block begins at the vertical origin with 0 potential energy and ends at rest where it has 0 kinetic energy. Now we can set these equations up. We have the total mass here, because remember, all of this in part 2, they've combined already, okay? So we have the initial kinetic energy of all this stuff equals the final potential energy of all this stuff. Now, you'll notice that we have these two masses added together on both sides, so that one term in parentheses will cancel out, no problem. Now, all we have to do is just a little bit of algebra to isolate our initial velocity. Okay, and we've done that here. So the initial velocity of this two object swing up is just the square root of 2gy final. Now we can actually take this, and I'll go back. We can actually take this because this initial part of the energy problem is the final velocity in the momentum part. Okay, so now we can take those two equations and combine them. Okay, so this was the statement for my momentum part. This was the statement for my energy part. And remember, we did momentum first and energy. The end of the momentum problem was the beginning of the energy problem, but we've superimposed those two equations to get this. Now, the last thing is essentially how do we determine the gained height? Okay, so we still need to figure out h. That's the only thing we're lacking. Now let's look at my diagram I have over here. So we want to know the height gained, which I've marked here in orange. Okay, that's our h or our y that we're calculating for. So we have to be a little clever. What we can do is we can take the whole string length, which I've shown here in green. Okay, so if we take the whole string length in green and then subtract off this final height, this y final, okay, I've marked it in blue. If we subtract off this y final, well, if you just look at the arrows, the green minus the blue gives us the orange. Okay, and that's actually what we're after. So let's figure out how to calculate the green and the blue and subtract those. Well, The green that's just the length of the string. Okay, well we know that. And then if you look over here at our diagram, well we know the hypotenuse of this triangle that this string is making is L. If we take the cosine, that's going to give us this blue piece. That's just L cosine theta, because that's the adjacent piece of this triangle. Okay, so if we take the difference of these two things, okay, I'm just going to do a little algebra here. Okay, well, I can pull the L out, so it turns out the length times 1 minus cosine theta, well, that's actually our height gain. That's our final height that we're after. Okay, so I can actually plug that in to my y final, and I get this nice equation here that actually works on all ballistic pendulum problems. So all the problems like this, you can use this equation for. Now to answer our original question, we can just plug in the values. We know the mass of the bullet, the mass of the wooden block, gravity, the length of the pendulum, and it turns out in our case from this initial problem, the bullet actually was traveling at 320 meters per second when it hit this block and caused it to swing up by some final height here. So just a quick summary. We do have kinetic energy, which deals with motion. Okay, and it's got its definition here, 1/2 mv squared. We have potential energy associated with position, and it's just mgy. So essentially, you could think about it as the force due to gravity, mg, scaled by how high something is off the ground, that y direction. Okay, so kinetic energy can be transformed into potential, and potential can be transformed into kinetic. And then under some circumstances, again, that's lack of friction, the mechanical energy K plus U is conserved. All right, so again, sorry this lecture is a little bit longer. Just remember the next few lectures should be much shorter. So I'm going to front end load what we're going to talk about and then sort of focus on some examples then following lectures. So as always, if you need any help with anything while you're working on problem sets and labs, please let me know. Otherwise, keep doing what you're doing.